the Hooke's law, and also we will study the simple harmonic motion. And we will learn how to get the spring constant using the simple harmonic motion. So let's get started, guys. So this figure represents Hooke's law. So as you can see here, guys, you can see that we have spring, and this spring has initial length, as you can see here. So this is the initial length, but after we added weight, we can see that the length like stretched, as you can see here. And after we added another weight right here, so we can see that the length stretched a little bit more. So this is Hooke's law, guys, and Hooke's law can be described by this equation. So force is equal to spring constant, so here we need to have minus sign, times x. So x is the change in length. So here if we have like, for example, L0, and here we have L1, and here we have like L2. So the change in length here, guys, between L0 and L1 is L1 minus L0. So that can give us, for example, x1, which is corresponding to the mass m1, for example. Yeah, and here we have L2 minus L0, which is x2, and it's corresponding to the mass m2, which is this mass. Yeah, and we can continue adding those masses, and then we will have like a table like this. So we have mass, we have x, the change in length, so we can have like more than one data point. And then what we can do, guys, we can multiply this mass by the gravitational acceleration to get the force, and then we can plot force versus change in length, and then we will have behavior like this, guys. So we can see that the force is increasing with increasing distance. If we continue to add those masses and never stop, so by the end of the day, this curve will be like this. It will continue to increase up significantly. So we don't need to achieve this point here. We don't need it. We are interested just in this part. Yeah, when the force is increasing with increasing, when the distance or the change in length or the change in spring length is increasing with increasing the applied force. Yeah, of course, you know, guys, there is applied force here. It works downward, the gravitational force. So that's great, and the slope of this behavior, guys, is equal to the spring constant. So this is a way to find the spring constant. There is another way, guys, to find the spring constant, which is called the simple harmonic motion. Maybe I can increase the size or the font of this pencil, of this pen, sorry. Yeah, so maybe that works, guys. So here, as you can see, guys, we can see that omega, maybe this is too much, so what I will do, I will have something. Yeah. So as you can see here, guys, from this equation, so what we have here, we have a mass. This mass is connected to a spring. And then what happened is the following. We raised this mass up, and then we released this mass. And what we can see here, we can see that the mass continued to oscillate ups and down, ups and down, ups and down. And that will create this kind of sine wave behavior. And by studying this sine wave behavior and solving a differential equation that I don't prepared to derive that. Just I prefer to have this result here, that omega is equal to square root k over m. So we can find from here, so omega is equal to square root k over m. So that's great, and omega, guys, is equal to 2 pi over t. So t is the periodic time. We can square this side, and that's equal to k over m. And from here, guys, we can have k is equal to 4 pi squared times m over t squared. So what is t? T is the periodic time. So what we will do, guys, in our in the second part of our experiment is to find the periodic time t, and then we can find the spring constant using this method, which is the simple harmonic motion. But the first part is right here, guys. We will use Hooke's law to find the spring constant. Yeah, it is easy, guys, and it is not complicated. Just what do we need to focus on? We need to focus on these two equations here. Just these two equations, guys. F is equal to minus kx, so this represents Hooke's law, and omega is equal to square root k over m. Yeah, and from here we got this equation, which is k is equal to 4 pi squared m over t squared. So this is great, guys. These are the equations that we will use in today's experiment. It is interesting to know the spring constant. So what I will do, guys, I will show you the material that we will use in today's.
Hi everybody, I hope that all of you are doing well. So today we will do lab number 5, and for lab number 5, what do we need? We need these things, guys. We need these weights. So 1, 2, 3, 4, 5. So we need these 5 weights, and those 5 weights are equal weights. We need this weight, which is heavier than these 5 weights. We need balance, and we will need two springs here. So one of them is A, so the longer one is A, and the shorter one is B. Yeah, so balance and some weights and 2 springs. So what we will study, guys, in this lab, we will study the following. So we will study the simple harmonic motion, and we will try to figure out the spring constant using the simple harmonic motion. And then we will compare that with Hooke's law. So also we will use Hooke's law to figure out the spring constant. So yeah, so let's see that and see the difference between these two ways to figure out the spring constant. So let's get started. So what I will do right now, guys, I will start with weighting those weights and see what we will have. So let's move them right here. So as you can see here, I used those washers as weights. They work very well. So I will use them. They won't be the same weight, but they give us like equivalent weights. And this is enough. And these are the 2 springs that we will use. This is spring number 1. Sorry, this is spring A, and this is spring B, and we will use them, guys, in today's experiment. So keep them here, and we will start with the heaviest one, which is this one. So we have like 13 washers here, so we will see the weight, guys, here, I will weight it in ounces, and then I will convert it to grams or kilograms. So let's see, what do we have here. So we have 9.6 here, we have 9.6 9.7 ounces here. Okay, I can see like 10.1. Let's wait for some time, maybe. So 10.1 ounces. 10.1 ounces, yeah. So let's write weight number 1 is 10.1 ounces. So that's great. I can also see like 10.2. Should be stable. Oh, we need to have 0 here before we wait. So let's do that right now here. So what we have 9.2. Great. So it is 9.2, guys. I apologize for the mistake. So we have 9.2 ounces. 9.2 ounces. So this one is 9.2 ounces, and this is the heaviest weight that we will use today. So this is number 1. Okay, so that's great. Now let's move to these and see what do we have. So for this, oops, we have 3.4 ounces. We need to make this 0 again. So let's see. 3.3 ounces. That should be 0. So this balance is not accurate enough, but I will try to do my best to get accurate weight here. So 3.2 ounces. Yeah, so that's great. That's strange. I will try to. Maybe this balance needs to have like stable. Needs to be horizontal, maybe. So maybe it can be here. Yeah, or maybe we can just remove this fabric right here and put it right here, guys, so that can give kind of stability. So maybe that can give some stability here. Have it 0. Yeah, so now we have 0. Let's try again. So let's see what we have. So 4.1 ounces. Yes. So weight number 2 is 4.1 ounces. Okay. Let's now move to the next one. This one, let's see what do we have. So we have 4 ounces here. So number 3 has 4 ounces. So this is number 3. And then let's check this. We have 4.1 ounces. Number 4. We have 4.1 ounces. So this is number 4. That's great. Let's now weigh this. So we have 4.3 ounces. So weight number 5 is 4.3 ounces. And weight number 6, which is this one, it is 4.3 ounces. So we have 4.3 ounces. So this is number 6. So this is great, guys. So these are the weights, as you can see here. So this is the heaviest one. This is 9.2 ounces. I'm going to measure it again, just to double check. Let's see. So we have 11.1 ounces. I will remove it. Oh, do that again. So I have 11.1 ounces. Yes. Yeah, so here, yeah, I think the balance should be, so we have 11.1 ounces. So these are the weights, guys, that I will use. So that's great. Let's now move to the next step. So we'll start, guys, with studying Hawk's Law. So here we have spring B. I think it is a good idea to start with spring A. So this is spring A. It is hanged right here. So this is spring A. What I'm going to do, guys, so this is the original length. I will increase the weights, and then we will measure the length of the spring. So let's do that, guys. So what we have here, so I will start adding those weights in the same order. So let's see, what do we have here? Oh yes, so this is weight number 5. So that's great. So this is number 5. This is number 2. This is number 3. So I will add them in order. So this is number 4. So let's start with weight number 2. So I will add it right here. So let's do that, guys. So this is weight number 2. And then we can add weight number 3, just gently and slowly like this. We don't need any vibrations here. Keep it stable. So that's great. And then I will add weight number 5 right here. So this is weight number 5. So there's kind of movement. We don't need any movement here, guys. Great. Sorry, so that was weight number 4. I will add now weight number 5. So now we have weight number 5. We don't need any oscillations here. So that's great. And then end up with weight number 6. So what we will study here, we will study changing the weight and changing the length of the oscilloscope, of the spring right here. Great, guys. So we know the original length of this spring, and what we will do, I think I will try to use Logger Pro to figure out these lengths, guys. So let's do that. Yep, so we are done with this part. That's great. Yeah, now what do we have, guys? Now we have spring B. And now we will apply the same thing, guys. What we will try to do, we will add weights and then see the change in length of this spring. So just to remind you, so this experiment is called studying Hooke's law. So this is what we are doing, and we will compare the spring constant that we will extract from this method with the simple harmonic motion, and we will see what do we have. So I will start adding weights here. So I will start with weight number 2. So we have 2. Do that slowly. So 2. So here I won't add like too much weights here. I will try to add the weights that, so we don't need any vibrations here. I will add weights, and at the same time I will maintain the flexibility of this spring. I don't need to destroy this spring, guys. So now I will add the other weight, which is number 3. Let's see what do we have here. So that's great. You can see that the length of the spring changed. And then I will move to number 4. So this is weight number 4. I don't need to destroy the flexibility. I think this is enough, guys, to use 3 weights here, because if I increase this weight, I might destroy the flexibility of this spring. Keep it balanced here. So that's great. So now, guys, we are done with the spring number 2, or spring B. So now what I will do, I will move to the simple harmonic motion. So we are done with studying Hooke's law. Now, guys, we will study the simple harmonic motion, and to do that we need to use the heavier weight right here, as you can see, and we need to hang it right here. So that's great. So that's great, guys. So now we have the weight right here. What I'm going to do, I'm going to lift this weight up and then release it. So this is the simple harmonic motion. Great. That's great. That's fantastic, guys. I'm going to stop it. So now we are done with this spring. I will move to the next spring right now. So this is a spring A. So I will move now to spring B. So this is spring B, and we will study also the simple harmonic motion. So to do that, we need to hang this weight right here and release it slowly, slowly, great, like this. And then we need to raise this weight up and then release it to have this harmonic motion. Yeah, so that's great, guys. I think we are done with the harmonic motion for this spring. So this is spring B. This is spring B. So now, guys, we are done with taking the measurements. So now we will move to Logger Pro to start collecting the data.
The first, I will try to analyze this video um, and work on the first part of today's experiment. So let's do that, guys. Well, so what we need to do, guys, we need to keep the video running until we achieve. So we'll start, guys, with the study box until we achieve the second that we are looking for. B. I think it is a good idea to start with spring A. So it should be here. It is hanged right here. So this is spring A. What I'm going to do, guys, so this is the original length. I will increase the weights, and then we will measure the length of the spring. So let's do that, guys. So what we have here. So I will start adding those weights in the same order. So let's see what do we have here. We'll just move it a little bit forward until we achieve the second that we are looking for. Should be somewhere. Yes, it is right here. Here. So let's do that, guys. So this is weight. So before we do that, guys, we need to know. Yeah, so we need to know the initial length of this spring. So this is spring A. And what I did, guys, I just measured the initial length here, and I will use it as a standard here in this video. So what I will do, guys, I will go to the set scale and have this distance right here is equal to 0.05 meter, which is the length of this spring, the initial length of this spring. So click OK. Yeah, and then what we will do, guys, we will add weights and then measure the length. So let's do that, guys, and you can have your pencil with you right now, so you can write down this data. So you need to create table, and this table has two columns. So the left-hand side column is the mass, and the right-hand side column is the change in length. So let's do that, guys, right now, and you can start collecting the data right now. So what I will do, I will move this, as you can see. or we can just start the guys. So this is weight number 2. Yeah, great. So you can see that there is change here in the length. So here, so what do we have here, guys? So I converted the 4.1 ounces for weight number 2. I converted that to kilograms. So what I got 0.116233. So this is the weight of weight number 2, which we have here. So 0.116233 kilogram. So let's see the corresponding length here, guys. So the corresponding length here should be, needs to be measured using this. So let's do that. I think before I measure, I think it's a good idea to have a reference here. So what I will do here, I will have my origin right here. So I can have a reference, for example, when I measure. So that's great. So let's measure this and see what do we have here. So this length, guys, is 0.05797. I will write that down. So what we have here, we have 0.05797 meters. Great. Let's now move to the next weight, and then we can add weight number 3, just gently and slowly like this. We don't need any. And you can see, guys, that the length of this spring changed again. So that's great. So now stop and then move to the ruler and measure this length, this new length here. So let's see what do we have here. So what do we have, guys? Here we have 0.06746 meters. 0.06746 meters. So that's great. Now I will move to the next one. And then I will add weight number 5 right here. So this is weight number 5. And the length is changing. So there's kind of movement. We don't need any movement here, guys. Great. So stop this and then go to the roller and measure this length, guys, like this. So what we will have here, so we have 0.07509. We have 0.07509 meters. So that's great. Let's continue. Sorry, so that was weight number 4. And we'll add now weight number 5. So now we have weight number 5. We don't need any oscillations here. So that's great. And then end up with weight number 6. So what we will study here, we will study. So oops, I think we need to have another data point here before we add weight number 6. So I will go back. So we don't need this weight. actually, yeah, we need to measure this before we add the other weight. So let's go to the ruler and then measure this distance here. And what we got here from weight number 4, from adding weight number 4, we got 0.08274 meters. So that's great, guys. And actually, I think, yeah, I will show you the masses of these weights, guys. So, you can see here that we need to sum up all of these weights. Weight number 2, 3, 4, 5. We need to sum them up when we talk about this particular data point. So I will show you that, guys, but let's finish here. So I will move to number 6. So what we will study here, we will study changing the weight and changing the length of the oscilloscope. Sorry, of the spring right here. So great. So this is the last weight that we need to add. So that's great. So let's now measure the change in length here. So what we got, here, we got 0.09132. So 0.09132 meters. Yeah, and here, guys, I will tell you the corresponding masses here. The first data point, which is 0.05797 meters, so the corresponding mass is 0.116233. That's great. And for the second data point, so we have length 0.06746, and the corresponding mass is 0.229631 kilogram. The third data point, we have distance 0.07509 meters, and the corresponding mass is 0.3458642 kilogram. The fourth data point is 0.08274 meters, and the corresponding mass is 0.4677671. For the last data point, we have length 0.09132 meters, and the corresponding mass is 0.589671. So that's great, guys. So we are done with this part, which is great. Try to write down these numbers, guys, and create table that has two columns. So the left-hand side column is the mass in kilograms, and the right-hand side column is the changing in length in meters, of course. Yeah, so this is spring A. Now let's move to the next spring. Yes, so now, guys, we have spring B, and now we will try to get some data from here. So let's do that, guys. So what they will do, the first thing that they will do here, I will set scale here, and I know the initial length of this spring, so it is 0.016 meters. So that's great. So we set scale. Now what I will do, I have the origin right here. So that's great. Now I will, yes, I think we need to work from here. Yep. So we have to do that slowly. So 2. So here I won't add like too much weights here. So that's great, guys. Just we don't need these oscillations. I will keep the video moving until we. I will try to add the weights that, so we don't need any vibrations here. I will add weights, and at the same time, I will maintain the flexibility of this spring. I don't. Yeah, so the spring now is ready, so we can measure this distance, guys. So the weight that we have here, guys, the weight that we have here in kilograms, so we have 0.116233 kilograms. So write that down, please. 0.116233 kilograms, because you will use that in your worksheet. So now let's measure the distance, guys, from here. Let's see, what do we have here? Yeah, so the distance that we have here, we have 0.3813 meters. So here, so the original length, guys, here is 0.016 meters. And after adding this mass, we got 0.03813 meters. So that's great. Let's move now to the next way to destroy this spring, guys. So now I will add the other weight, which is number 3. Let's see, what do we have here. That's great. You can see that the length of the spring changed. And then I will move to number 4. So this is weight number 4. I don't need to destroy the flexibility. I think this is enough, guys, to use 3 weights here, because if I increase this, we need to go back. I apologize. So I have to measure the length for the second one. It should be somewhere right here. Yes, so this is the second one. I will move to number. Yes, so this is the second one. Now I will measure the length of this spring again. Let's see, what do we have here. Yeah, so here we have 0.05. We have 0.05784 meters. So that's great, guys. And this change in length, guys, is corresponding to this weight, 0.229631 kilograms. 0.229631 kilograms. So that's great. Now I will move to the next weight, and let's see the change in length. 4. So this is weight number 4. I don't need to destroy the flexibility. I think this is enough, guys, to use 3 weights here, because if I increase this weight, I might destroy the flexibility of this spring. Keep it balanced here. So that's great. So now, guys, we are done. Great. So now I will measure the length after adding the third weight. So let's see, what do we have here. Yeah, so what do we have is 0.08011, 0.08011 meters. So that's great, guys. So now we are done with this. So we have the whole data. Just to remind you that the corresponding mass for the third change in length is 0.3458642. So this is great. Yeah, so this is great, guys, and you have to do this data that I collected with you right now. So guys, don't copy the data that I will post. The data that I will post is just to help you guys to see the final results. But for you, you need to follow the video and then get these numbers. So when you submit your worksheet, I will make sure that you use these numbers, the numbers that we collected right now. So don't use, guys, the numbers that I used in my data. So I will show you the spreadsheet, the Excel spreadsheet, and I will show you my work on this experiment. So, but for you guys, you need to use this data, please. So use this data that we are collecting in your worksheet. Yep, so we are done with this part. Now let's move to the next part, guys. So this is the next part, guys, of the lab, and now we will try to get the periodic time for the simple harmonic motion for spring A. So we will start with spring A. So let's get started here. Now, guys, we will study the simple harmonic motion. Um, but before that, I need to do all of these steps. So I need to set scale like this. So the length of this spring is 0.05 meters. So that's great. And let's see, we need the origin. So the origin should be, I will choose the origin to be right here, guys. Yep. So I think everything is great. So we can start. To do that, we need to use the heavier weight right here, as you can see, and we need to hang it right here. So that's great. So that's great, guys. So now we have the weight right here. What I'm going to do, I'm going to lift this weight up and do great. So let's go back. I need the second that my hand. Yes, so this is the second that I'm looking for. So now, guys, what I will do, I will follow, yeah, let's choose this point, guys. So we are not interested in X, but we are interested in time. So that's fine if we started from here. So we'll do that. Start here. And see what kind of harmonic motion do we have. Let's see, so you can see that the harmonic motion started to appear. Okay. Okay. So 1, 2, 3. We need just another one. That's great. Yeah, so that's great. I believe we have here this harmonic motion, guys. So you can see that. So how many periods do we have? We have 1 period, 2, 3, 4. We have 4 periods, guys. So now let's see the time. The time for these periods is equal to, I will have it from here. Yes, and go like this until here. So this is the time, guys, and I need to go left. Yeah, so this is the time for 4 revolutions, for 4 periods. So let's write that down. So what we have here, guys, so here we have 29.86, and here we have 31.06. So we need to subtract. So T4, the time for 4 periods, as you can see here, is equal to 31.06 minus 29.86 seconds. And that's equal to, so I will try to calculate this, guys. I will just look for calculator. Yeah, I think I have calculator somewhere here. Yes, I got a calculator, so let's calculate that, guys, together. So what do we have? We have 31.06. So let's write that down. So 31.06 minus, let's go here to the other end here. So we have 29.86. And that's equal to, guys, 1.2 seconds. So this 1.2 seconds is the time for these 4 periods. For these 4 periods, guys. So yeah, and you can see here that delta t is equal to 1.209. So we can get that also from here. So that's fine. Yep, so this is one thing, guys. So we got that. So we can consider 1.209 as we have here in lower pro, 09 second. But to get the time for 1 period, which is t, what do we need to do, guys? We need to do the following. So we need to divide 1.209 divided by 4. So that's equal to, so the time for 1 period is equal to 0.30225 seconds. So that's great, guys. So now we got the periodic time for 1 period for spring A. So that's great, guys. You need to have this. And also, guys, I would like to share with you that the mass, the heavier mass that I'm using here is equal to 0.314697 kilogram. This is the mass that I'm using here, which is the heavier mass, so you can use it. I will show you my data, and as I mentioned, please don't copy my data. I hope that you follow what we are doing here and write this data down, and from this data you can finish your worksheet. The data that I will show you by the end of this lab is just to help you to imagine what kind of result you will have. Great, so we are done now with this part. So what I will do now, guys, so I will move to the next, step, which is doing or studying the harmonic motion for spring B. So let's do that, guys, together. Okay, so now, guys, you can see that we will start studying spring B. So, and we will get the periodic time for spring B. So let's do that, guys. I will look for spring B, and we will study also the simple harmonic motion. So to do that, we need to hang this weight right here and release it slowly, slowly. Great. Like this. And then we need to raise this weight up. Okay, so now let's, before we do that, guys, we need to go back. We need to have the original length here. We need to set scale first. So let's go back here. So let's set scale here. So what I will do now, yeah, I will set scale. So I know that the length of this spring, yeah, so that's wrong. I need to have correct length here. So that's great. It is 0.016 meters. So we did that. Great. So now let's start the video. So to do that, we need to hang this weight right here and release it slowly, slowly. Great. Like this. And then we need to raise this weight up. Okay, raise it up. I need this moment here. When I release my hand. So that's great. So now I will set my origin right here. So that's great. And then what I will do, guys, I will start studying this motion. So let's see what will happen here. Yeah, so this motion is different, and you will see, guys, that we will have like a little bit longer, shorter, maybe a little bit shorter or longer. No, it should be longer periodic time. Yeah, we can see that from this harmonic motion. So it is very slow harmonic motion, and that's why the periodic time should be a little bit longer. Yeah, so what we will do, guys, as you can see here, so we have this harmonic motion. So that's great. It is right here on the right hand side. So that's great. We need another period, and then we will be done. Yeah, so we have 3 periods. We still need another period to have 4 periods at least. Yeah, so 4 periods looks good, and they are enough because you know there is damping here, and this uh, harmonic motion will be reduced. So that's great, guys. So we can come here and do the same thing. Guys. So I need to actually here I don't need Y. Actually, no, I don't need X here. Yep, we just need Y. So let's see here. Yep. So maybe we can have like 0.01. Yeah, so that's great. So now I can start from this point and then move to that point to include 4 periods here. And you can see, guys, here that um, uh, the periodic time or the total time for these 4 periods. So let's see here. So we have 1 period, 1, 2, 3, 4 periods here. And for these 4 periods, what do we have? We have T4 is equal to, as you can see here, guys, this number right here. So delta T is equal to 1.974 seconds. So you have 1.974 seconds. So this is for 4 periods, as you can see. To get the time for single period, so what we need to do, we need to divide this number, which is 1.974. We need to divide that by 4. So let's do that. So this is the calculator. So I will do that right now. So we have 1.974 divided by 4. So that's equal to 0.4935 seconds. So yeah, so this is the periodic time for one period. So that's perfect, guys. We are done. Let's create comparison. So now we are done with the data that you will use. But the comparison that I will show you, it is from my data, the data that I did for me. So please, guys, use the data on this video, but don't use the data that I will show you. Just I would like you to use new measurements. So what I will show you is just something to compare your work to my work. That's it. So yeah, these measurements that we did, these are new measurements, and these are for you guys. The measurements that I will show you, just a minute, just a minute. So these measurements are the measurements that I did. So, and as I mentioned, I will provide you these measurements just to compare your data with my data. So that's great. So we are done with this part, guys, which is great. Now let's move to the next step. Yep, okay, so as you can see, guys, on the right-hand side, this is the data that you need to use to figure out the spring constant. And the left-hand side data is the data that I used. So these was my measurements to figure out the spring constant. So for you guys in this worksheet, you need to use this data. So you can use these masses, 116,233 kilogram, 0.229631 kilogram, and etc. And here for this table right here, so you can use also these masses. But for the x, you need to use these distances, guys. And don't forget, when you plot, yeah, let's go here to the plot. Yeah, when you plot, guys, as I did here, so you need to plot your data as I did right here. So when you plot, guys, you need to consider x that, so x is the new length minus the original length, as you can see here. Maybe I can make it a little bit bigger for you guys. Yeah, so I can do that. Yep, so the original length, the new length minus the original length. So that can give you delta x, this delta x right here. So this delta x is L minus L0 or x minus x0 as you would like. And when you plot delta x with f, so delta x represents x-axis, and the force F represents y-axis. And also, by the way, you need to multiply this mass by gravitational acceleration to get the force. So you need the force. So because you need to plot force on y-axis, and you need to plot the change in length on x-axis. So that's great. So this is spring A. So this is for spring A. Now let's move to spring B. The same thing for spring B, guys. For this delta x, you need to subtract the original length, as you can see here, 0.016, from the new length. So you need to subtract this original length to get delta x. And then you need to multiply this mass by gravitational acceleration so you can have the force. And then you need to plot, as you can see here, you need to plot force versus change in length right here, and you can get the spring constant. So right here for spring B, we have 51.57, and using Hooke's law, of course. And for spring A, we have 139.81 kilogram per second squared, of course. So this is the spring constant for spring A. So that's great, guys. And I will show you my data right here. Just a minute. So this is my data, as I mentioned. So maybe I can make it a little bit bigger so you can see, guys, what I got here. Maybe we can make it a little bit smaller. Yeah. So this is what I got, guys. So you can see that from Hooke's law, I got for spring A, I got 139.81 kilogram per second. This is from the slope, from plotting force versus change in length, and from the harmonic motion, I got 137 kilogram per second squared. For spring B, I got 51.571 kilogram per second squared. I apologize, this one should be second squared, I'm sorry. And from the harmonic motion for spring B, I got 49.64 kilogram per second squared. So for you guys, what do you need to do, guys? For you, you need to use this data, this new data that I got for you. So you have X for spring A, and you have X's here for spring B, and you have the original length for spring B and the original length for spring A. And also you have the periodic time right here for spring A, and the periodic time right here for spring B. So what do you need to do, guys? You need to use the equations that I mentioned, the equation that I mentioned in the first part of today's lab. So I know today's lab is a little bit long. So by the end of this lab, guys, I would like to thank you. I will send you the worksheet so you can start working. But for now, once you receive the video, I would command you to start working on plotting these plots and finish these calculations. Actually, guys, you won't have any worksheet. So the worksheet will have two questions. The first question is to determine the spring constant for those two springs using Hooke's law, and then compare them